Today we're going to be working with common logarithms. A common logarithm is a logarithm that has base 10. For example, we could write that as log 10 of 1,000 equals 3, or we could just write it, because it's a common log, as log of 1,000 equals 3. When it's a common log, we don't actually put the base 10 at the bottom of the logarithm. In the old days, back when I was in high school, we had to do this using tables of values and scientific notation, because we didn't have calculators that had a logarithm button on them. So for example, if I were working the problem, the log of 50,000, the first thing I would do is I would rewrite that problem as 5 times 10 to the 4th power. Now, using the properties of logs, because that's a multiplication property, that's going to be the same as the log of 5 plus the log of 10 to the 4th, or the log of 5 plus 4 log of 10. That would be using the power rule, and the log of 10, log base 10 of 10 is 1, so it would be the log of 5 plus 4 times 1, or 4 plus the log of 5. What we would have done is this. We would have looked up the log of 5 from a table, and we would have gotten 0.6990. That number was called the mantissa. And then we would have looked at the exponent, which is 4, and the 4 is called the characteristic. We would have added those two things together and gotten 4.6990. On your calculator, you simply have to go find the log key on the left-hand side of your calculator, hit log 50,000, enter, and it will tell you how to do it. Now, let's say, for example, we were looking at this problem, log of 5 times 2 to the 3rd. We would use a lot of the different properties of logarithms to work this. First, we would break it down into the log of 5 plus the log of 2 to the 3rd. Then we would have taken the power rule and dropped the exponent in front and made it the log of 5 plus 3 log of 2. We would then have looked up the log of 5 in our table. We would have looked up the log of 2 in our table. We would have multiplied the log of 2 by 3, added those two things together, and come up with the log of 5 times 2 to the 3rd is 1.6021. Now, if you look at the practice problems below, you can see that I've asked you to use the dark ages method for 5 to 7, and then come back and check them with your calculator, and then to do problem number 8. So go ahead, pause the podcast, give it a try, and then we'll come back and check your work and your solutions. Checking our work on these problems, on number 5, 80,000 was 8 times 10 to the 4th, so I added the log of 8 plus 4. Number 6, 0.003 was 3 times 10 to the negative 3rd, so I added the log of 3 to negative 3. And on number 7, 81 was 3 to the 4th, so that was 3 to the 4th times 10 to the negative 4th. So when I did that problem, I added 4 logs of 3 to negative 4. I did forget to put the parentheses around these when I wrote it in log form. Let's go ahead and be sure we put those in there so that you understand to use the product rule for logs. Now, on the number 7, the answer is off a little bit on the decimal, and that's because I used a rounded number on the 0.4771, and when I added the negative 4 to it, when I checked it on my calculator, I was off by 1/10,000th. On number 8, I simply typed it in. Now let's look at graphing logs. When you're graphing logs, we do have an issue with the domain, and that is that logs are only defined when the value is greater than 0, because the log base 10 of anything to a power is going to be some number greater than 0, because no matter what power we put on the right hand side, it's going to be 10 to that power. So this has to be some number greater than 0. Right here. Needs to be some number greater than 0. So that means we're only going to be able to shade when the log is greater than 0. So I have to do the domain issue. X minus 4 had to be greater than 0. So when I complete this problem, that means I'm actually going to have a vertical asymptote at x equals 4, and I'm going to only shade to the right of 4. Now, simply what I would do is type this into my calculator, look at the graph, get some numbers from the table, and copy it onto the paper. Notice one thing on here, the graphing program I was using, you could not show that this was a broken line. This should have been a broken line going along there, not a solid line. So we had the graph, and it was only shaded to the right of 4. Here's a problem for you to practice. Go ahead and try it. You can use your calculator, and then be sure you shade it appropriately. Notice on this function, the basic log graph was moved 3 places to the left, so instead of going through 1, 0, it went through -2, 0. It was a solid line because of the less than or equal to, and when I tested the point 0, 0 into the problem, I ended up with a true statement, so I shaded underneath. Again, my domain was x plus 3 had to be greater than 0, so x had to be greater than -3. So there is a vertical asymptote over here at -3. Now, the problem with the logs that you were working with before is they weren't in base 10, so we couldn't use our calculator. We have something called a change of base formula, which allows you to change into base 10. You can change it into any base you want. Now, the reason we like this is because if we do it, we can use the calculator. So it's simple to do. You simply take the log of the result, that's the log base b of n, divided by the log of the base, and that will change the formula. So as you see in this problem, I changed it to the log of 172, that was my result, divided by the log of 8, which was my base, and I ended up with 2.4754, and that would be the log of, that's what the result is. 8 to the 2.4754 does equal approximately 172. So you can check that on your calculator. Try out these 2 problems, and then we'll move on. Hopefully you set up your problems correctly. We're able to type that into your calculator and come up with the logs of 1.1632 and 1.3023. Notice whenever we're evaluating logs, we usually round to 4 decimal places. Now, sometimes it's easier to work the problem by getting rid of the logarithm, and in that case we want to use what we call the anti-logarithm or anti-log, and to access this on your calculator, you push second log. The anti-log is actually like raising each side to making a power of 10. So it's basically saying 10 to the log of 1 over x equals 10 to the 0.065. That's essentially what it's doing, because the inverse of taking a logarithm is to raise 10 to that power. So we started with the problem, log of 1 over x equals 0.65. Then I took the anti-log of both sides, or just pushed second and log, and I ended up by, what that does is that eliminates the log. And after the log was eliminated, I had 1 over x equals 1.161. I multiplied both sides of the equation by x and solved the result and got approximately 0.861. It was actually approximately 0.8610, and we really should put that 0 in front of the decimal to keep our significant figures correct. Now, we can actually use logarithms to solve exponential equations, and this is where it's most useful. Before, if we had an exponential equation and the bases weren't the same, we couldn't really work with them. Now we can work with things that don't have the same base. So we're going to start with this example. The first thing we're going to do is we're going to take the log of both sides. Now, when I take the log of both sides, then I have the log base 10 of 6 to the 3x equals the log of 81. At this point, I can use the power rule. In other words, I just take that exponent, drop it back in front of the log, and I have 3x times the log of 6 equals the log of 81. Then I'm going to simply divide both sides by 3 and log of 6. That way I can cancel out the 3's, I can cancel out the log of 6's, and I end up with x. Now, when you evaluate this on your calculator, be sure you put the denominator in parentheses, entirely in parentheses, and notice how your calculator opens and closes parentheses. Remember, the newer ones, some of them will not have the parentheses after it says log. The older versions will all open a parentheses as soon as you type in log and then the number. Once you punch this into your calculator, we evaluate it, and our answer is 0.8175, or 0.8175. Now, moving on, it's time for you to practice some. So we have some problems here. There will be a couple of these that I will go over specifically with you because I know they're going to be a little bit trickier. So let's go ahead and give them a shot and then pause the podcast and come back in. There's a little something of interest I'd like to point out in these two problems. Notice in the first one there's only a variable on the left on number 13. On number 14 there's a variable in the left and the right, and it did affect the way I worked the problem just slightly. It didn't have to affect it totally. I could have done it a little bit differently on the left side one, but this actually was the easier method. First, I took the log of both sides, and then I used the power rule to drop the exponent in front. This is where I could have made a difference. I could have done the distributive property and distributed x to the log of 2.2 and then negative 5 to the log of 2.2. Because there was not a variable on the other side, I chose to just go ahead and divide it out first. That's how I ended up with this step where I have the log of 9.32 over the log of 2.5. Then I added 5 to both sides. This made my problem calculator ready, and I just typed it directly in. Again, your calculators will more than likely open parentheses after the log. Be sure you close it before you divide. Now, the next problem, the difference was the variable on both sides. Because of the variable on both sides, after this step where I used the power rule, where I dropped the exponents down in front, I actually had to use the distributive property because I'm going to need to get all the x's on one side and all the constants on the other. So I had this step right here where I distributed. After that, what I did was I don't know why, I just like my constants to be positive, so I moved the 2 log 6 to the right, I moved the x log 4 to the left. That's what's on the next line of my equation. Then I factored out the x right here, so it was x times the log of 6 minus the log of 4 equaled 2 times the log of 6. Did the division, again, be very careful about your parentheses, and ended up with x is approximately 8.380. Try the next two problems. Looking at these two problems, the one on the left is fairly simple. We simply take the log of take the log of both sides, use the power rule, and we end up with x is less than 2.9709. However, this part comes from the definition of a logarithm. It only exists if x is greater than 0. So I had to make it 0 is less than x is less than 2.907. I had to give it that left side limit. The other problem is considerably trickier. One, it's easier to work if you change it into exponential form, or excuse me, rational exponents. Then we have to use the product rule. Then we have to use the power rule. Then we have to distribute. Then we have to move things to both sides. And then at this point right here, I chose to eliminate the fraction. So I multiplied both sides of my inequality by 4. That gave me this long, complicated thing. Then again, I had to use the distributive property in this line. And again, move everything to the other side. I had to move the log 4 to the right, divide both sides by 4 log 3 minus log 4, and ended up with my final result of x is greater than or equal to 4.8434. In this case, I did not have to add in the greater than 0 because it already was. This concludes our